Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
It's really wonderful to see all of you here. Pleases me very much. I think you're going to enjoy this. The film that you're going to see is about a dream of time travel and how this dream has obsessed two men who had different visions that had the same root. H.G. Wells' The Time Machine. Afterward, what I will do will actually move from here to the gallery, and I'll have a short discussion, additional discussion, about the science of time travel for all of you who are able to stay. And then I'll have a Q&A, and I'll introduce a special guest, another special guest, and there will be a book signing as well, okay? So that's the arc of what we're doing. I'll let the movie speak for itself, but I'm going to open it by using a quote, sort of a paraphrase of one of my favorite TV science fiction. Sit back, relax. You are about to experience the awe and mystery that reaches from the inner mind to the outer limits. And before I talk a little bit more about the science behind time travel, and it's not going to be a long discussion, but I want to fill in some blanks that weren't mentioned in the film, I want to make a few acknowledgements. First, I want to thank Real Artways for screening the film. I really appreciated that. And I also want to thank, of course, the director of the film, Jay Shield. He did a fantastic job, and it was a pleasure working with him. And this now has been screened everywhere. In fact, in April of this year, it'll be screened in Graz, Austria, and I've been asked to go there to host it in Austria. So it's really getting international attention, so I'm very proud about that. The other person who is my fellow actor, he's making a guest appearance here, Rob Miosi. You stand up. Oh, there he is. Okay. So during the question and answer period, you'll have a chance to ask him questions as well as me. Okay. And then I want to acknowledge the scenes that were taken at the laboratory at the University of Connecticut. That laboratory is directed and owned by Professor Chandra Roy Chowdhury, please. And Chandra has been wonderful to work with, and I'm really pleased, and thank you, Chandra, for allowing me to do that. And you'll notice there was a gentleman who was helping me with that apparatus. It's a demonstration apparatus for the ring laser, okay? He was a former graduate student of mine, and now he's a faculty member at Quinnipiac University, Rob Fischetti. Rob? Oh, okay, great. And also, I should mention that this involved lasers a lot, you notice. The thing is that I got my PhD in physics from Penn State University. There are Penn State people here also in the audience. But the thing is, my PhD was in Einstein's general theory of relativity, things like black holes and wormholes and things like that. And my first job, however, was here in Connecticut at United Technologies, and I was assigned to work at Pratt & Whitney. And as you might expect, they did not want me to work on black holes. What they wanted me to do was something very, very practical. What they wanted me to do was to have a mathematical model for drilling holes using lasers and turbine blades, okay? And I was very, very fortunate that the person who hired me, taking a chance on someone who was way out there to do this, was Dr. Gerald Peterson, who headed the theoretical physics group in the research center, and he is here. Jerry, please. And I hope, I'm not sure whether he was able to make it or not, but one other person that I'm deeply grateful for, you notice there was a scene that took place in a hospital there, okay? And this is when I did have a very serious heart episode. The person who detected that was a very astute cardiologist who detected that and brought me through that so that I'm able to appear here today. Is Dr. Parveen Khanna, and I don't know if Dr. Khanna is here in the audience, was able to make it. No, but the thing is that I was very, very grateful for him. So now the thing is that you already know the motivation that I had for wanting to travel back in time, and that still is something that, I mean, it's funny, people sometimes say that, do you still feel that connection? I think of my father every single day, even though it's been decades since he passed away. There's not a day that I don't think of him. And the thing is that he was just a wonderful man, and I still miss him every day. The thing is that, of course, as was mentioned in the film, this is what changed things for me. This allowed me to dream about the possibility of traveling back into the past to see him again. But I realized eventually that it was going to have to be real science. And that real science, this is actually the first popularization that I read about Einstein. And in it, it said, it was 12 when I came across this at a Salvation Army bookstore. We were very poor after my father died, and I used to hang out. I had a very serious book habit. And I used to hang out at the Salvation Army for books. And when I saw the cover of this one, I knew that Einstein was this great genius. And incidentally, to me, it's always been an interesting coincidence that Einstein died the same year my father died, in 1955. But when I saw the cover of this, that he was standing next to an hourglass, this spoke to me immediately that Einstein had something to do with time. And so when I read the book, even though it was a popularization, it was rough going, but I did get the essence that Einstein said that there are ways that you can, in fact, alter time. And so I wanted to know those ways, but what I realized, it was going to be a very, very, very long journey before I did. But eventually I came to understand that Einstein did say that there are two ways of altering time. They were mentioned in the film. One was mentioned explicitly, and that is Einstein's special theory of relativity, which says that time for a moving clock slows down. The faster you move, the more time slows down. Now, your heart is a clock. This means that it would slow down the faster you move. You wouldn't notice it, but it would happen, okay? The thing is that we know that this is so by the experiment, for example, that I mentioned in the film, at the Naval Observatory in 1971. That was a real experiment where they flew a passenger jet around the world at the speed of sound and brought it back and found that the clock had actually slowed down fractions of a second. It wasn't as dramatic as one would expect because the effect depends on speed. The faster you go, the more time slows down. Now, you might say the speed of sound is very, very fast, okay? It's roughly 740 miles per hour. But when you compare it to the speed of light is 1,000,000 times faster than the speed of sound. And when we have rockets that can go close to the speed of light, we will actually find this effect to be very, very dramatic. Years will pass for someone who maybe is a couple of years will pass for someone who's traveling close to the speed of light, but for people on Earth, decades could pass. And literally, we could find astronauts coming back if they have families younger than their children or grandchildren. This is a beginning of it. We've seen the beginning of this, okay? Now, however, my work was based not on Einstein's special theory of relativity, but on Einstein's general theory of relativity. That wasn't mentioned as much explicitly in the movie, and I want to highlight that a little bit because that was actually the key to my work. Now, what is it that Einstein did, and what is the general theory of relativity? Incidentally, it took Einstein 10 years to develop that theory, and I'm going to explain it to you in a lot less time than that. But the essence of it is the following. It had to do with a whole new theory of gravity. And what do I mean by that? Well, according to everything that we've learned in school, there's a gravitational force between an object. Imagine this is the sun and this is the earth. Then there's a gravitational attraction between the sun and the earth that keeps the earth in orbit around it. Einstein said that's not right. That's an illusion. What's really happening is that the sun is affecting the empty space around it and the earth is moving in. What do I mean by that? Well, this device down here, and you may have to stand up to see it because it's not going to fit on this right here. So people in the back, you can actually even, okay. Well, this, if you want to hold, I mean, I don't, it's because the table is just not, yeah. You have to have an experimental physicist, by the way, to help you all the time. Okay. All right. This device, yeah, there, you know, it's both a theoretician and experimenter. Now, this device right here is a trampoline for leprechauns. No, what it is, it's what's called a gravity platform. And what this surface represents is empty space, okay? And this represents the sun. What Einstein said is that the sun is actually bending empty space around it. We can't see it, of course, because it's empty, but this is what it's doing. And what the Earth is actually doing is, let me give it a little sideways motion. Notice, it's orbiting, like a skater on a roller derby ring, okay? Can you see that? That's Einstein's general theory of relativity. All it says is that what we call the gravitational force really isn't a force at all. It's actually the bending of empty space, and the Earth orbits that. That's it, okay? Now, of course, what he did was he used equations for this. The equations he used were very, very complicated, called Einstein's gravitational field equations, but this is the correct visualization of his equations. Thank you, gentlemen. Oops. Don't want anything to happen to the Earth here. So, to reiterate, this is the essence of Einstein's general theory of relativity, that the sun will bend empty space and the Earth, okay, moves in that. Now you might say, how did we know that? Well, the proof of it was the prediction that Einstein made, which was that, let's suppose that the sun is here and this is a star that's behind the sun. So normally we would not be able to see this star because the sun is in the way. But because space is being bent, then this starlight will actually get bent as it's coming by the sun. So it will seem to us as though the star is out here rather than really here. That means you would actually be able to see stars that would be blocked by the sun because of the bending of space by the sun. This was actually observed during a solar eclipse in 1919 by a physicist named Eddington. This was the first prediction that showed us that space really is affected by massive objects. Now, in Einstein's theory, space and time come as a team. You can't really have one without the other. Whatever it is you do to space also happens to time. That means if space gets bent, then time also gets bent. Now, what do I mean by bending of time? Well, in Einstein's theory, a bending of time would show up to us as time slowing down in a gravitational field. According to Einstein, the stronger gravity is, the more time will slow down. Now, you might say, well, hey, have we seen anything like that? Not only have we seen it, but what most people don't realize is part of our everyday life. What do I mean by that? Well, you probably recognize this device. It's in my car, and you probably may have it in your car. What is it? You know? GPS. A GPS. This device would not work without Einstein's theory. Let me show you. Right now, 12,000 miles above us, there are 24 satellites in what are known as geosynchronous orbits. That is to say, 3 of the satellites are covering any particular patch of Earth. The way that your GPS system works is the following. These satellites at a certain time send a signal. Your unit has a clock in it. So the satellites send a signal at a certain time. It reaches the unit in your car at a certain time. The speed of the signal is the speed of light. So by knowing the time the signal was sent, knowing the time the signal was received, and the speed of the signal, you can actually calculate distance. That's how it's done. When they were setting up the system, however, it was giving locations all over the place. What was happening? Well, when the engineers consulted with physicists, what they realized is that they were taking into account Newton's theory of gravity. And according to Newton's theory of gravity, nothing can affect time. Not gravity, not anything. And they were using that as the basis. But remember, what Einstein's theory showed is that time slows down in a gravitational field. You have to realize that gravity is stronger here at the surface of the Earth than it is at high altitude where satellites are. That means, according to his theory, that the clock in your unit is actually running slower than the clocks on board these satellites. What they have to do is use computers to calibrate for that difference. And when they did, the system was working perfectly. So this is a definite demonstration that gravity affects time, okay, in a very practical way. So the next time you're in your car, keep that in mind, that you're actually seeing a demonstration of Einstein's general theory of relativity. The thing is that, and for me, the fact that the unit works correctly, I like to think of it in the physicist's way of looking at this, that without Einstein, we'd really be lost. Now, my breakthrough, which was mentioned in the film, was that in Einstein's theory, in Newton's theory, the only thing that can create gravity is matter. The Earth creates gravity, which keeps us in orbit. The Sun creates gravity, which keeps us, in orbit, and so on. The thing is that it turns out that in Einstein's theory, not only does matter create gravity, light can create gravity as well. And as I mentioned, that's where my breakthrough came in, okay? Because I realized that, remember, gravity can affect time. But if light can create gravity and gravity can affect time, then light can affect time. And that was my breakthrough. What I did was I solved Einstein's gravitational field equations, not a trivial thing. And what I found was the following. This is what was also mentioned above. This device is called a ring laser. Okay? It's just simply a laser. This is a semi-transparent mirror. These are totally reflecting mirrors. So you have a light beam coming through here, reflecting here, reflecting here, reflecting here. So this is what I mean when I'm talking about a circulating beam of light. It just goes round and around and around. And as was mentioned in the movie, the analogy you can think of is having a cup of coffee. And if you think of the circulating light beam as being like the spoon, and you think of the space in here as being like the coffee, then the circulating light beam, the energy of the circulating light beam, is actually going to cause this empty space to get twisted around. And you can't see it, of course, but if you put in a neutron, a subatomic particle called a neutron, then as the space is getting twisted, it will drag the neutron around. And as I said, I solved Einstein's equation. I'm showing you pictorially, but this is what I did. And I found That was one prediction. What I also found was that if this twisting of space is strong enough, remember, space and time are linked. Whatever you do to space also happens to time. That means that time will actually get twisted. Now, in the movie, it implied almost that that time does normally go in a straight line from the past, present, to the future. And if you twist time into a loop, you could go from the past, the present, to the future, and then back to the past. But it almost implied that you would be going around and around. It's a little bit more than that. And this illustrates it. This little device is a slinky. And what's happening is that when you turn on the circulating beam of light, as space is being twisted, time will get twisted in a loop. And remember, the Earth is moving in space. So what's happening is that these loops in time are not going back on themselves. As the Earth and the apparatus move in space, the loops in time are like the links on this slinky. In other words, these loops in time move with the Earth. So if here's the Earth at some later time, here's the Earth at some past time, you can spiral along these loops in time to any point where the Earth was, all the way back to when you turned the device on. So this is what I mean when I say that you create loops in time, okay? The experiment has to be done, both the space twisting and the time twisting. As was mentioned in the, unfortunately, these things are not like you see in science fiction movies. They are expensive, very expensive. And we're in the process of trying to raise the funding just to show that we can do the twisting of space. But this is the beginning of that. Now, I should also mention, it was mentioned very well in the movie about the fact that there are paradoxes that are associated with this. And the thing is that one of them is the grandfather paradox, which was mentioned. When you go back into the past, you could create a problem, like, for instance, erasing your own existence potentially. What wasn't mentioned in the movie is the fact that physicists have actually come up with a way around this paradox. Okay? That wasn't mentioned. And how do they come up with that? It has to do with a notion that's almost as bizarre as the notion of time travel itself. It has to do with the notion of what are called parallel universes. Back in 1957, a physicist at Princeton named Hugh Everett III applied quantum theory is the other pillar of modern physics. Relativity is what we've been talking about. Quantum physics is the other pillar. And in some ways, quantum physics is stranger than relativity. But quantum physics is behind all of our modern technology. Your cell phones, your PCs, all of these things work because of quantum mechanics. Okay? We wouldn't even understand why the atom is stable without quantum mechanics. It's real. However, this physicist applied the notion of quantum mechanics to the universe as a whole. And what he found was that there's this aspect of quantum mechanics which you can't predict exactly what's going to happen. You can only predict the probability. And when he applied quantum mechanics to the universe as a whole, what he found was that for every decision that you make, that decision and its opposite will both occur, but in different universes. For example, suppose that at dinner this evening, you were trying to decide, looking at your menu, what it is that you want to have. There's two different selections that you have. Well, you decide you're going to choose this. At that instant, there's a split of the universe. There is also you in a parallel universe who has chosen the other thing on the menu. They don't know about each other, and they're real. And they are moving both into space, in a whole different space. Not our space, it's called a superspace. This means that for every single decision that is made, and this doesn't have to do with just simply human beings. In other words, if an electron has a possibility of going along this path or along this path, there will be a split of the universe in which the electron will go along this path, but in another universe along this path, okay? Very weird. But it also answers, you may be familiar with a very, very famous baseball great. His name was Yogi Berra, okay? And he did what people have called yogiisms. That is to say, he would make statements that seemed to defy, common sense. One of his most famous statements was, when you come to a fork in the road, take it. Okay? Well, actually that statement makes sense in quantum mechanics. You can come to a fork of the road and take it, okay? I also always feel that this notion of parallel universes could lead to an interesting philosophy of life, because whatever it is that I do here, I know in some universe I got it right. Okay? So this notion of parallel universes was taken over by another physicist named David Deutsch at Oxford University. And what he did was to apply this notion to time travel. And what he found, working it out mathematically, was that when you travel back into the past, at the moment you arrive in the past, there's a split of the universe. You arrive in the past of a parallel universe. In that universe, you could actually do something like preventing your grandparents from meeting each other. You would just now find yourself in a weird universe that you were never born in. But remember, there was a split. That other universe you don't arrive in. And that other universe leads to your grandparents meeting each other, having your parents, and your parents having you. So the upshot is that time travel to the past is possible, but the past you arrive in is not the past that you came from. So which is it? Is this going to be the way in which it is? We don't know until we actually do the experiment. But this is one of the ways in which this grandfather paradox resolution has been addressed, okay? So what I'm going to do now is to have Rob, you can also, I'm going to have Q&A, open this up for a question and answer period, and you can ask me, anything you like, and Rob, anything that you like, okay? So let's do that, okay? Yes?
Hello, Professor.
Hi.
So if you were to create the lasering devices outlined here, what would manifest success? What would you actually look for that would say, aha, this works or it does not?
That's an excellent question. The thing is that the way in which we would do it in a real engineering way, okay, would be the following. We know that there are subatomic particles that can only live for a very short period of time and they disintegrate, okay? The thing is that normally if they're moving fast enough, they will live longer, okay? What we feel is that if we put these subatomic particles into this device, they will actually go back in time a little bit and then live through time again. So they will actually come out a little older than they were, which means that they will live shorter than they normally would. So we know exactly what they normally live, but we could actually alter that. Now, and you might say, why is it that they would be older? Well, imagine this if it was in terms of a human being. If you travel back into the past, when you arrive in the past, and let's suppose you continue to live your normal life, then if you do, when you get back to the future again, you will be older than you would have been if you had not gone back to the past, okay? And that's what happens with subatomic particles. So that tells us if we can actually see that we can change the lifetime of these particles, that will be the first thing. But eventually what we would like to do, and we're not talking about doing this with human beings, is to send information and messages back. Imagine if we could send information back to tell us about natural disasters like tsunamis and earthquakes, the lives we could save, okay? So that's one of the things that we're interested in, is trying to see if we can send information back to the past. That's our ultimate goal.
Yeah.
Yeah, well, all kinds of information can be detected, okay? But that's the way in which we would do it, okay? And as I said, we're not trying to do it with human beings, but which is more important. In fact, sending information is in many ways more important. Good question. It's another, yeah. Thanks, Kim.
You said that when there are massive objects in the universe, they tend to bend light.
That's right.
And that's how gravity works, by bending the fabric of space.
That's exactly right.
Where do graviton particles come into play?
Okay, very good question. The thing is that, remember I said that there's this other pillar of physics called quantum mechanics? What people have felt is that just like light is made up of particles of light, we see light as continuous, but we know it's made up of particles of light called photons. What people have felt is that the gravitational field might be actually made up of particles of gravity. These particles of gravity are called gravitons. Okay, so essentially that comes from quantum mechanics. Quantum mechanics is the thing that told us that light was made up of particles. When you apply quantum mechanics to Einstein's theory, you find out that it says that you could actually have particles of gravity. Okay, we haven't detected those. The most recent thing we've detected are gravity waves, and that comes from the fact that if you look at this sheet that I was talking, if you hit it, you notice that it will vibrate. Okay, well, what they found is that if you have orbiting black holes, these orbiting black holes will actually cause space to vibrate, and that's what we call gravity waves. So gravity waves are not normal waves; they are actually waves of space itself, and those were recently detected. But so far, we haven't detected the particles. Oh, okay, is that answered? Okay, you had a question too? Thanks again, Kim.
If every single event in the universe, whether it be an electron or a human ordering a meal, or so on, would it be true that there are infinite universes created by this?
That's exactly right. But they're not happening in our universe, but they are separate universes that are happening in what's called a superspace. But you're absolutely right. It implies that there's an infinite number of different possible universes.
And a second question, if we are able to transmit information back to the past and prevent an event from happening, wouldn't that cause us sending a message to live in, would that just create a parallel universe where the event didn't happen?
That's right.
Okay, so it wouldn't happen in our time.
No, it's not as simple as that. Yes, it could be that the information goes to a parallel universe, and what we do is help that people in that universe. However, nature and reality are very strange. It could happen, although it boggles the mind, that when we do that, we are giving up the reality that we are used to, and we will be living in a new reality, okay, in which that event didn't happen, but there will be that ripple effect that affects everything. We don't know which of those two things are actually going to occur. And it does create a problem, because once we do get information from the future, we have to ask ourselves, is this information coming from my universe, or is it coming from a parallel universe? So it raises a whole set of issues that we're going to have to address when we actually do it.
And the final question, is this only applicable to sending stuff back, or could it be used to send stuff forward too?
Oh yeah, well, there's actually no problem with sending things forward. Okay, as a matter of fact, we do that without thinking about it right now. You sent information to the future, and I got it. But in a sense, even though you didn't think about this, the information that you sent from you actually arrived in my past, because it took time for that information to travel from you to me. So I didn't really get it instantaneously. I got past information. And you know that the sun out there is 93 million miles away from us. It takes 8 minutes for light to get from the sun to the earth. That means that throughout our entire life, we never see the sun the way it is now for the sun. We see the sun as it was 8 minutes ago. Okay? Yeah.
Thanks, Dr. Mallett. Two questions. One, did the number of sides on the polygon change the results of the experiment? Because
No.
you got 4, but I would think it's a continuous result.
It doesn't matter.
Okay.
That's just to simplify the
Yeah, yeah,
mathematics.
okay.
What I did in a second paper was to actually look at a cylinder of light.
Right.
And it has the same effects. It's just that, you know, it changes. Oh, well, I don't have that equation up there. It changes it like a numerical factor, but the same effect happens, is right.
And then, so massive objects like black holes, are they essentially time machines?
That's right. Because remember that since gravity affects time, you can just pass it
And
forward.
then, so
Yeah.
what's going on inside
A black hole? Oh. That is a question that's, thank you, that's still at the frontier of physics. We have no idea what's going on inside of a black hole because light can't get out. That's why it's called a black hole. Consequently, we don't have any information of what's going on. But if you got close to a black hole without going in, time will slow down more and more and more. So you could actually use a black hole as sort of a natural time machine as long as you didn't go inside. Yeah. It's actually more complicated because if that's for a non-rotating black hole. If it's a rotating black hole, there's actually trajectories that you could take that could allow you to go partially into the black hole and come out in the past. Yeah. I should mention because I don't have time to go into all of this today, but I've published, there's a book called Time Traveler that I talk about a lot of these things that I didn't get to today. For example, I didn't go into wormholes, I didn't go into details of black holes, cosmic strings, and the book is actually written at a popular level. There's, but it goes into a lot more detail about time and about things that can affect time, and it goes into more detail about my past life, the good, the bad, and the ugly, as to take a phrase from Clint Eastwood movie. But the book, and I actually I have copies of the book for a book signing at the end of this for people who are interested. I have them at a discounted rate, by the way, so you might want to grab a copy. Yes. Yeah, thanks, Tom.
Hello, my question is, as you are simultaneously doing this project, are you thinking of sensors? How will you get the information that you're transmitting through this light beam? And also, piggybacking on this, how we, the information that we get from our, go out there, that you get from your dreams, the connections you make with this person who said, he thought of you and you got the information delayed later. How can you be sure that you're not getting information currently? And how are you sensing that and how you...
Well, we are. I mean, I am getting information from the past all the time. All I have to do is look up into the night sky. There are stars out there that may not even exist anymore. But the thing is that the light that left them 10,000 years ago was still in transit. So I'm actually seeing something that may not even exist out there anymore. Okay, so that is actually one other aspect of it. Now, as far as receiving the signals, you actually have to have an apparatus to detect the past. So, and sometimes people forget that because they expect that a time traveler would just appear. You can't. They have to appear into something. Okay, and I actually tell people that they have to be careful about that because you hear a lot of these stories about time travelers from the distant future. They say that I've come from the distant future, and I always tell my students, when that happens, first be very polite. I think my therapist would say that too. Be very polite, and then say, okay, please show me the device you've materialized in. That usually stops it right there, okay? All right, so you can pass to Tom. I think there's some questions over here. Yes.
Mine is a much more general, broad one. But what advice would you give as a way we can get more children to be interested in science and to follow in that?
Well, to do what families here are doing, bringing their children to events where they know that it will be a popular level event, okay? That's one way of doing it, is to actually show your own interest. I mean, what was it that my father did? I mean, the thing is that my father gave me scientific toys. Like, he gave me as toys a gyroscope, a crystal radio set, a chemistry set. He gave me the things that he knew would be, and he just didn't hand it to me. He didn't say, here, Ron, have this gyroscope. What he did was he said, isn't it strange that when it's spinning, it can stand on its top, but whenever it stops spinning, all of a sudden it falls off, I mean, the thing is that he would get into it with me. That's the way. And you just actually have to be an example. And if you are, then not only will that help stimulate them, but that will also bond you closer to them because they see that you're interested in them. My father worked 2 jobs, so he wasn't able to do this all the time, but the time that he did it is now our buzzword in our time, quality time. That is the thing that made me so in love with him that I've spent my life trying to see him again. Does that make sense? Oh, okay. Robin back there? Oh, you have a question and then, okay. Oh, yeah, no, fine.
I'm curious, first of all, it's a beautiful and moving film. And I'm curious to know if, or what's next for you. I'm not going to ask you how much it costs, but I am curious to know. There must be this immense void after completing a project like this.
That's very astute.
Very astute
indeed. First of all, I wanted to say this is the most fascinating audience I've ever had.
I agree.
People interested in science and asking really interesting questions. There's another project I would love to do. It's also inspired by an H.G. Wells novel he wrote just at the turn of the century in 1900. It was called First Men in the Moon. At the time, helium was just discovered, and he used that as an excuse to come up with an anti-gravity paste. And so, thank you. Getting over a cold. So, this scientist invents this paste, and he's not a very practical fellow. He decides he's going to use it to take a trip to the moon. I would like to build a spaceship that he built. So it's a Victorian spaceship. It's a spherical device, but the interior of it is very Victorian. It's all plush velvet. It's quite beautiful. And when it's done, you should all come and take a ride to the moon with me.
My second question was, if this time travel machine is invented and your present or future self could go back to the guy who is starting out this project, what would you say?
First, I'd have to get myself a club. You know, it's hard to control. Well, that's a tough one. I know that this is all about controlling the future and the past. You know, we're compelled to do things, whether it's a good idea or not. It was a mixed bag for me. There were many good things that came out of this, and there were very torturous things that came out of this. But I don't think I would change anything. It was a really good adventure, and it ended up with me here talking to you fine folks, so it's been great.
Oh,
Good question.
okay. Oh, yes.
It seemed to me if you wanted to travel to the past, then you have to at least exceed the speed of light.
No.
No?
No. In fact, that's the difference between the special theory and the general theory. The special theory of relativity, to put it in a nutshell, it says that time is affected by speed. But it turns out that it's only in the forward direction. That is to say, you can slow time down. But it turns out that there's actually an equation that shows you that if you try to get at the velocity of light, boom, everything blows up, which means that you can't, okay? So no matter how fast you can go to the future, but you can't go to the past because you can't exceed the speed of light, okay? And there's reasons for this not exceeding the speed of light. It's sometimes people confuse it with like the light barrier, the sound barrier. It's very different than that. But the going to the past, in the general theory of relativity, you don't have to exceed the speed of light. All you have to do is warp space and time enough to travel back. And it's that warping of space and time that does not happen in the special theory of relativity that allows for the possibility of time traveling to the past. And as I mentioned, I'm not the only physicist looking at. There's a man at Caltech. His name is Kip Thorne, and he looks at the possibility of using wormholes to travel back. And there's a man at Princeton, Richard Gott, who's looking at what are called cosmic strings as a method. So these are all, but they're all based on Einstein's theories of relativity. That's the other thing I caution people. If the work has a scientific basis in Einstein's theory, then it should be taken seriously. If not, then it should be suspect. And we know that Einstein's theory is right. We know that it works, from everything from the atomic bomb to, cosmology, the expanding universe. So that's an important thing to keep in mind. But that's the difference. Okay? Yes.
I have two questions. My first question, after having watched the documentary, I noticed there's like a humanistic element that has to do with spirituality. And so, thank you. So my initial question is, with regards to that notion of spirituality, what did you have to tap into during the duration of, I guess, building, well, your research and with the establishment of the notion of creating this time machine? What elements of spirituality did you feel like you had to tap into with, I guess, the consideration of time travel and science?
No, that's a good question. One of the things that I want to point out, and everyone has their own beliefs, but I want to point out that I actually am a believer, okay? But that isn't what I tapped into, okay? What it was the emotional intensity of my feeling of my loss for my father, okay? That's what I tapped into, and that's what kept me going. You know, and that's, as I said, I have this picture of him behind the television set, and I pass it every day, and even when I'm not passing it, I think about him and all the questions I would like to have asked him. So that's my connection. The connection is an emotional connection, but that doesn't mean that I don't have a spiritual side of my personality, but that isn't what motivated.
And my second question is, also after watching the documentary as a filmmaker myself, I noticed that there is the notion of how you were influenced by H.G. Wells. And I wanted to ask and this is extended to both of you, if you noticed that has your work influenced, I guess, the concepts or new productions of cinema moving forward? Have you noticed that your research and the things that you've studied have had an influence on cinema?
Well, I know that there's some producers in the audience, and maybe that might influence them, but we'll see, But yeah, no, it's influenced people in the cinema. One is this documentary, but as I said, there have been some interest in a regular feature film of it with major actors playing it. For me, that would be neat to see my father in that. I mean, to actually have someone play my father, because that's not something that has happened in any documentaries, because no one can, by nature of a documentary. But yeah, I mean, the thing is that. And I'll let Rob answer, because he's been involved in the film industry directly. But as I said, for me, that started the inspiration with it. But we'll see. I'm hoping that eventually there will be a regular feature film associated with it.
I believe that Spike Lee was interested.
Well, was.
Oh, okay.
Yeah, no, the thing is that what happened is that Spike got involved in other things. Mm-hmm. And the thing is that he did finish a script, but there were issues, okay? And the thing is that he's no longer involved with the project.
Right. Well, let's hope it happens.
Well, the thing is, I think it will. Yeah. I mean, there's a lot of other great directors and producers besides Spike Lee.
And it's a really fascinating story.
Oh yeah, thank you.
As far as how this has affected filmmaking, I think storytelling really hasn't changed much since, people are scraping images on cave walls. The thing that changes it mostly is just technology, right? So pretty soon we'll be watching 3D holographic actors will be in the holodeck or on the Starship Enterprise, but I don't think things have changed that much in the way of storytelling.
Yeah. No, and it's interesting that Rob mentions this thing. The most recent movie, which was eerie in its way, if you haven't seen it yet, I can recommend it. It's the new Star Wars, Rogue One, because they actually use digitalized actors who are no longer with us. And you can't tell the difference. And that's, I think, is going to lead to some interesting things in the film industry in the future.
Let's take a minute or two to tell us about how you guys came together and how this movie came to be.
Well, yeah, sure.
Well, the internet is a weird and wonderful thing. I was working on the machine, and Jay Shield, the film director, was interested in doing a film about the interest in time travel. If you Google time travel, you get 800 million pages of something that doesn't exist yet.
Yeah.
And he got in touch with me And then in the process of making the film, he told me that Ron was going to be involved, and I had heard Ron's story on This American Life.
Yeah.
And I was thrilled. And he said, I'm going to have Ron come over. And I thought, what the hell am I going to talk to a theoretical physicist about? That conversation will last about 2 minutes. Well, as it turned out, Ron and I sat in my backyard for about 3 hours. And we could have talked for 3 hours more because we found that many of the things that inspired him inspired me, and vice versa. So, for example, it was like, he told me, I just bought the box set of The Twilight Zone. And so that was an hour of conversation right there. So, it's really interesting. It's like science and art and imagination kind of coming together. So that's how we met.
Yeah. And in fact, there is a very famous quote by Einstein, which says that imagination is more important than knowledge. Knowledge is limited, but imagination encircles the world. And he didn't mean that knowledge wasn't important. What he meant was that it's our imagination that leads us to want to get the knowledge, okay? So I think that's important to keep in mind about imagination being our driving force.
So that being said, Professor, your imagination, how could, all of us would want to see this experiment manifest. How could individuals support it in some way? Is there a Kickstarter type thing, GoFundMe?
The thing is that, as a matter of fact, the University of, I've been very pleased that the University of Connecticut has supported. They actually have a University of Connecticut Foundation. The nice thing about that is the fact that the funding doesn't come to me, okay? So people don't have to worry that I'm using it to go to Acapulco for vacation. The funding actually goes to them. Not only that, because it's a nonprofit, it's tax deductible. So any donations that come to the foundation, they'll be tax deductible. If people really are interested, they can go to my website, and the project is called Space-Time Twisting by Light. And any amount is something we've raised about 11,000. It's still far from $250,000, but still it's been people, who have been donating. And as I said, it is tax deductible. That's the main thing. And I'm hoping that because of the publicity that it's getting for documentaries like this, and I hope eventually a feature film, feature film, a Hollywood feature film, that will raise the profile of it, and that eventually we will get the serious money that we need. But for now, that if people wish, they can contribute to the University of Connecticut Foundation. And as I said, they can go on my website at UConn, and it has a little thing there that says funding.
And so donations can be earmarked towards your project?
Oh yeah, in fact, the project is called Space-Time Twisting by Light. That's the designation of the project. And as I said, the funds go directly to the foundation, and you get a nice letter thanking you, and you get my thanks. So, okay, thank you. Yeah.
I just would like clarification. Earlier you were saying that you could go back in time. You believe that strongly believe that you could go back in time,
right,
and talk to someone in the past, like you were saying, your father. So if you're able to go back in time and talk to your father, are you saying that that's in this universe or in a parallel universe?
I don't know.
Okay. And how would you be able to confirm which universe?
I'd have to do the experiment. We'd have to set up experiments to actually determine whether we're changing things in this universe or if it just disappears and changes something in a parallel universe. That's a very complicated level, but that's what we would have to do, is figure out how to do that. Okay, so we don't know.
Okay,
at this point.
So if it's in a parallel universe, you can...
Yeah, you can do anything in a parallel universe.
Yes, so you'll be able to still pass the information on to your father, but
it wouldn't
you
help.
wouldn't be able to affect what's going on in this particular universe.
That's right.
So it's two paths that are moving at the same time, but they'll never cross.
That's right. That's right. That's exactly right. Okay.
Just had a question, something you said that was really interesting, and I'm just curious, as a scientist, how do you reckon scientific understanding with belief system like spirituality?
There's no conflict whatsoever. I mean, the thing is that we are multifaceted, okay? And trying to understand the physical world is one aspect of that, okay? And to me, that's me, part of me. That is not the all of me. The other parts of me have interests just like everyone else, you know? And the thing is that that's what makes us what we are, okay? What happens sometimes is people think that these things have to contradict. If you do the one, it blocks out the other. That's not so at all. And if you look at the biographies of famous physicists, and I mentioned some of those biographies in my book, you find that these people are as different from each other as everyone else. But they had one thing that was in common, a passion to understand how the universe works. But they were very different. I mean, some were from the Jewish faith, some Lutheran, some Catholic, some agnostic, some atheists. I mean, it was just like the span here that we live with. But as I said, they're unified by one passion. That's the same for all of them. How does this universe work? Okay? All right, I want to thank everyone. These are really a wonderful crowd. You're absolutely wonderful crowd. And thank you so much for being here. And as I said, I will have a book signing for people who are interested at the conclusion of this. So one thing I want to say, though, is that even when we do master time, I think it's important for all of us to keep in mind that the only thing that we really have is our present moment, okay? And we should make the best of that present moment. And I want all of you to enjoy your journey through time. Thank you.